For more than a century, humanity believed it had finally begun to understand the universe. We mapped the stars, discovered galaxies, measured gravity, split the atom, and walked on the moon. Slowly, humanity started building a picture of reality itself, a cosmic architecture that seemed elegant, mathematical, and predictable. For the first time in history, it felt as though the universe was finally becoming understandable. The old myths faded, the ancient fears disappeared, and science began replacing mystery with equations. But today, something is wrong, very wrong. The universe is no longer behaving the way our models say it should. Galaxies rotate too fast, the cosmos expands too strangely, and the numbers refuse to agree. For decades, physicists have searched for an invisible substance they believe fills the universe, a mysterious entity known as dark matter. There's only one problem. No one has ever found it, not in space, not underground, not inside particle accelerators, nowhere. And now, some scientists are beginning to ask a dangerous question. What if dark matter does not exist at all? But the story goes much deeper than that. Hidden behind this cosmological mystery lies another idea, one so controversial and strange that many physicists refuse to even discuss it. The possibility that space itself may not work the way we think. That reality may contain another metric, another geometry, another structure of space-time. And if that were true, then the speed of light itself may not be absolute. Imagine two travelers leaving Marseille and heading toward Algeria. One travels through the air, the other through water. Now imagine both believe they are limited by the speed of sound. In air, sound travels at around 340 meters per second, but underwater that limit changes dramatically. Sound can travel more than 4 times faster. The limit itself changed, not because physics was broken, but because the medium changed. According to one controversial cosmological theory, humanity may be making the exact same mistake when thinking about the speed of light. For over a century, the speed of light became more than a scientific constant. It became psychological. A wall, a cosmic prison. Nothing can exceed it. Nothing can escape it. Nothing can go beyond it. The stars became unreachable. Interstellar travel became fantasy, and the galaxy became effectively closed. And yet, what if the real question was never, can something travel faster than light? But instead, what if different regions of reality obey different limits? At first, the idea sounds absurd, like science fiction. But surprisingly, it emerges from a growing crisis inside cosmology itself, a crisis so profound that some physicists now believe humanity may be approaching another scientific revolution. For decades, astronomers believed gravity was fully understood. Newton explained the planets, Einstein explained space-time, and the equations worked beautifully, until scientists started looking carefully at galaxies. Galaxies refused to behave correctly. Stars orbiting near the outer edges were moving far too quickly. According to ordinary gravity, those galaxies should have torn themselves apart billions of years ago. But they did not. Something invisible appeared to be holding them together. So physicists proposed a solution: dark matter, a mysterious invisible substance that would not emit light, reflect light, or interact with ordinary matter, but would possess gravity strong enough to explain the missing mass. At first, the idea seemed elegant, simple, and temporary. Most scientists assumed dark matter would eventually be detected. But the years passed, and dark matter remained invisible. 10 years, 20 years, 30 years, still invisible. Entire underground laboratories were built beneath mountains. Massive detectors filled with liquid xenon waited silently in the dark. Scientists searched for weakly interacting particles. Nothing. No confirmed particle, no direct observation, no undeniable evidence. And yet modern cosmology now depends on dark matter. Without it, many equations collapse. which raises an uncomfortable possibility. What if humanity created dark matter because the model itself was incomplete? Today, cracks are appearing everywhere, not only around dark matter, but inside cosmology itself. Different methods of measuring the expansion of the universe now produce conflicting results. The numbers refuse to agree. Physicists call this the Hubble tension. At the same time, another invisible concept entered the equations: dark energy, a mysterious force supposedly accelerating the expansion of the cosmos. Modern cosmology now depends on two invisible ingredients: dark matter and dark energy. Together, they supposedly represent most of the universe, meaning ordinary matter. Stars, planets, galaxies, human beings would represent only a tiny fraction of reality. Some physicists accept this without hesitation. Others are deeply uncomfortable with it, because at what point does a scientific model become too dependent on invisible corrections? At what point do we stop describing reality and start protecting the equations? That question lies at the heart of what some researchers now call the cosmological crisis. And this is where the story becomes controversial, because this is where one French physicist enters the picture, Jean-Pierre Petit. An engineer, scientist, researcher, and deeply unconventional thinker, Petit argued for decades that modern cosmology may be fundamentally incomplete, not slightly wrong, but fundamentally wrong. According to him, dark matter may not exist at all. Instead, he proposed an alternative cosmological model called Janus, named after the Roman god, with two faces, two sectors, two metrics, two forms of matter: positive mass and negative mass. At first glance, the idea sounds absurd, because negative mass creates paradoxes in classical physics. Push a negative mass object and bizarre runaway effects appear. The mathematics becomes strange, almost pathological. So most physicists dismissed the concept immediately. But Petit argued something important. The paradox only appears because humanity tries to force negative mass into equations built for a single metric universe. What if space-time itself possesses two structures, two geometries, two gravitational frameworks? In the Janus model, positive and negative masses belong to different sectors, different metrics, different geodesics, and different interactions. According to Petit, this naturally explains galactic rotation curves without dark matter. No invisible particles, no hidden substance, just geometry. And if true, that changes everything. Because now, the crisis becomes much larger than dark matter itself. Humanity must confront a terrifying possibility. What if space-time is more complicated than Einstein imagined? The deeper one explores Janus, the stranger the theory becomes. According to the model, the universe may possess a kind of invisible twin sector, not a parallel universe in the science fiction sense, but another metric, another side of reality, invisible to us. Photons associated with negative matter would themselves possess negative energy, meaning ordinary observers could never directly detect them. The two sectors become mutually invisible. Suddenly, dark matter transforms into something radically different. Not invisible particles hidden inside our universe, but an entire invisible sector of space-time itself, a hidden cosmic geometry. And this is where the philosophical implications become enormous. If reality truly contains hidden structures beyond direct observation, then humanity may currently perceive only a tiny fraction of existence. Not because we are unintelligent, but because our senses, and perhaps even our equations, are limited. For most of human history, people assumed reality was exactly what they could perceive. The Earth felt stationary, so humanity believed it was stationary. The sun appeared to move around us, so humanity believed the universe revolved around Earth. Again and again, science forced humanity to confront the limits of intuition. Perhaps the cosmological crisis represents another one of those moments, another confrontation between human certainty and reality itself. And now, we arrive at the most explosive part of the theory, the speed of light. For over a century, humanity treated the speed of light as the ultimate cosmic barrier. But Janus introduces another possibility. What if different metrics possess different limiting velocities? Remember the analogy. Sound travels differently in air than in water. The medium changes the limit. So what if space-time itself can possess different structures, different cosmic media, different limits? According to Petit's interpretation, the twin metric could possess a speed of light nearly 100 times faster than ours. But the implications go even further. The structure of space itself would also differ. Distances could effectively shrink. The famous factor of 1,000 associated with interstellar travel in Janus would not simply come from traveling faster. It would emerge from both higher velocity limits and shorter effective distances. Together, travel times collapse dramatically. Suddenly, the galaxy changes. The stars are no longer unreachable. The Milky Way is no longer an impossible prison. Civilizations separated by enormous cosmic distances could theoretically interact. And immediately another question appears. If interstellar travel becomes physically plausible, where is everybody? This is known as the Fermi paradox. Statistically, intelligent civilizations should exist. There are hundreds of billions of stars in our galaxy alone, and potentially trillions of planets. Yet humanity sees no obvious evidence of advanced extraterrestrial civilizations. Some scientists believe intelligent life is extraordinarily. Others believe civilizations destroy themselves. Others say interstellar travel is simply impossible. But Janus introduces another disturbing possibility. What if advanced civilizations do not violate physics? What if they simply learn to navigate another metric? Suddenly, ideas once confined to speculative science fiction begin touching cosmology itself. And whether Janus is correct or not, that intellectual possibility alone profoundly changes the way we imagine the universe. The cosmos becomes stranger, not smaller, larger, more mysterious, more unsettling. Perhaps that is why these theories fascinate so many people. They reopen the feeling humanity once had while staring at the night sky. Mystery. For centuries, modern civilization slowly removed mystery from the universe. Every equation explained something, every discovery reduced uncertainty. But now, cosmology itself appears uncertain again, and deep down, humanity is simultaneously terrified and fascinated by that possibility. Throughout history, science repeatedly resisted radical ideas, not because scientists are evil, but because human beings naturally defend stable systems. Copernicus shattered Earth-centered cosmology. Galileo Galilei challenged established doctrine. Albert Einstein shattered classical certainty. Quantum mechanics shattered Einstein's intuitions. Every scientific revolution begins the same way. Anomalies appear, the old model struggles, corrections accumulate, and eventually someone proposes something so strange that the establishment initially rejects it. This does not mean every dissident scientist is correct. Most revolutionary theories fail. But history reveals something important. Reality does not care about consensus. The universe obeys its own laws, not our preferences. In ancient astronomy, planetary motion became increasingly difficult to explain, so astronomers introduced epicycles. Circular corrections layered on top of circular corrections. The system grew more complicated, but preserved the central assumption that Earth remained at the center. Then one day, the entire framework collapsed. Some critics of modern cosmology now ask an uncomfortable question: could dark matter and dark energy become the epicycles of our era? Not necessarily false, but perhaps symptoms of a deeper misunderstanding. This possibility is what makes the cosmological crisis so intellectually dangerous. If the foundations are incomplete, then entire branches of modern physics may require reconstruction. And that is not merely a scientific problem, it is psychological. Careers, institutions, reputations, funding, and entire generations of researchers become emotionally attached to particular models of reality. Scientific revolutions are not purely mathematical, they are human events, yet skepticism also protects science. Extraordinary claims require extraordinary evidence, and many unconventional theories collapse under scrutiny. The scientific establishment is not irrational for being cautious. The danger appears when caution transforms into intellectual rigidity, when anomalies are ignored rather than investigated, when equations become more important than reality itself. Perhaps the greatest lesson of all is this: science is not certainty. Science is organized doubt, a confrontation between human imagination and reality itself. Every major breakthrough begins with a terrifying possibility, the possibility that we were wrong. Maybe dark matter exists, maybe future experiments will eventually detect it, maybe Janus is completely incorrect, maybe Jean-Pierre Petit will ultimately be forgotten by history. Or maybe humanity is standing at the edge of another scientific revolution, a moment similar to Copernicus, similar to Einstein, a moment where reality itself begins slipping beyond the boundaries of our current models. Because one thing is certain, the universe is still stranger than we imagined, and perhaps far stranger than we are capable of understanding. But before humanity reaches that conclusion, there is another layer to this story, because the cosmological crisis is not only about physics, it is also about civilization. For centuries, science gave humanity a feeling of stability. Every generation believed the next discovery would complete the puzzle. First Newton, then Maxwell, then Einstein, then quantum mechanics. Each revolution expanded reality, and each time, humanity believed the final theory was finally close. But cosmology today feels different. Not because science stopped progressing, but because the contradictions are accumulating faster than the explanations. The James Webb Space Telescope recently revealed galaxies appearing far earlier than many cosmological models expected, structures emerging too quickly, galaxies too massive, too organized, too ancient. Again and again, observations appear slightly ahead of the theory, not enough to completely destroy the model, but enough to create discomfort. And discomfort is often where scientific revolutions begin. One of the strangest aspects of modern cosmology is this: the more humanity learns about the universe, the less ordinary matter seems to matter. Stars, planets, nebulae, black holes, human beings. According to modern models, all of this represents only a tiny fraction of existence. Almost everything else would belong to invisible components: dark matter, dark energy, invisible gravity, invisible expansion, invisible structure. And perhaps that is why some physicists are becoming uncomfortable, because eventually one begins asking a disturbing philosophical question. If 95% of the universe is invisible and undetectable, then what exactly are we describing? Reality or mathematical necessity? That distinction matters enormously, because physics was never supposed to become mythology. Its power came from prediction, observation, experiment, and verification. And yet today, cosmology increasingly deals with entities humanity cannot directly observe. Jean-Pierre Petit is not the only scientist to challenge aspects of modern cosmology, but he represents something psychologically important: the return of the outsider physicist. For much of the 20th century, physics became institutional. Large collaborations, massive funding, gigantic particle accelerators, international projects. Modern science became extraordinarily powerful, but it also became increasingly centralized, and centralized systems naturally resist radical deviations. Again, not because of conspiracy, but because stability creates inertia. If an entire scientific ecosystem depends on a framework, abandoning that framework becomes emotionally and economically difficult. This does not prove Janus is correct, but it explains why controversial ideas struggle to survive. And perhaps this is where the public fascination with figures like Jean-Pierre Petit truly comes from. Not simply because of physics, but because people instinctively recognize the archetype, the dissident scientist, the individual standing outside institutional consensus. Humanity has always been fascinated by such figures: Galileo, Tesla, Einstein. Sometimes history eventually proves them right. Sometimes history forgets them completely. But culturally, they represent something powerful: the possibility that reality itself may still contain hidden doors. And maybe that is why cosmology fascinates humanity more than almost any other scientific field. Because cosmology does not merely describe stars, it describes our place in existence. If the universe is static, humanity thinks differently. If the universe is expanding, humanity thinks differently. If the universe contains hidden dimensions, humanity thinks differently. Every cosmological model eventually becomes philosophical. Every model reshapes civilization. The ancient Greeks imagined a finite cosmos. The medieval world imagined divine celestial spheres. Newton imagined mechanical order. Einstein transformed reality into curved space-time. And now, theories like Janus introduce something even stranger: a universe potentially layered with hidden geometries, hidden sectors, hidden structures of causality. One of the reasons the speed of light became psychologically sacred is because it created boundaries. Boundaries comfort the human mind. They define what is possible, what is impossible, what belongs to science, and what belongs to fantasy. But every major scientific revolution eventually destroys a boundary humanity once considered absolute. Before Newton, celestial mechanics seemed divine. Before Einstein, time itself appeared fixed. Before quantum mechanics, nature seemed deterministic. Then reality changed. Again, and again, and again. This is why the analogy between sound and light is so powerful, because it subtly shifts the problem. Instead of asking, how do we break the speed limit, the theory asks, what if the limit depends on the structure itself? That is a completely different philosophical framework, and if true, it changes interstellar travel forever, because suddenly the impossible becomes geometrical rather than mechanical. The challenge is no longer brute force, it becomes topology, metrics, space-time engineering. Jean-Pierre Petit himself spent years discussing magnetohydrodynamics, MHD, a field exploring the interaction between magnetic fields and conductive fluids or plasmas. In theory, MHD concepts could allow extraordinary aerospace effects, boundary layer manipulation, plasma control, hypersonic travel, reduced drag. To many people, these ideas sound futuristic. But MHD is real physics. The question is simply how far such technologies can ultimately evolve. And once again, the imagination of the public immediately jumps ahead. If humanity someday masters space-time metrics, what would become possible? Could civilizations spread across galaxies? Could relativistic isolation disappear? Could entire concepts of distance become obsolete? These questions feel almost spiritual, because at their core, they challenge the loneliness of the cosmos. For generations, humanity slowly accepted a tragic idea that the stars may remain forever unreachable, that intelligent life may exist elsewhere, but remain eternally separated by impossible distances. The speed of light became the wall separating civilizations. But theories like Janus reopen the possibility that the wall itself may be more complicated than expected. Again, this does not prove the theory, but it changes the emotional landscape of cosmology. And emotions matter, because science is done by human beings driven by curiosity, fear, wonder, and obsession. And perhaps no scientific field generates more existential emotion than cosmology. There is another reason the cosmological crisis matters: artificial intelligence. Humanity is now entering an era where machine intelligence may begin assisting scientific discovery itself. Future AI systems could potentially analyze cosmological datasets beyond human intuition. They may identify hidden structures, unexpected correlations, entirely new mathematical patterns. Already, modern cosmology produces unimaginable quantities of data: galactic surveys, gravitational lensing maps, cosmic microwave background analysis, dark matter simulations. The scale exceeds direct human comprehension. And perhaps this means the future of cosmology may not resemble the 20th century at all. The next Einstein may not emerge from isolation with pencil and paper. The next revolution could emerge from networks, algorithms, collective intelligence. Humanity may currently be standing between two revolutions simultaneously: a revolution in intelligence and a revolution in cosmology. And if both transformations collide, the consequences could reshape civilization itself. But perhaps the deepest emotional layer of this entire story is much simpler. Humanity wants meaning. For thousands of years, the night sky represented mystery. Ancient civilizations projected gods into the heavens. Modern civilization replaced mythology with equations. But the emotional need remained the same: to understand where we are, why we exist, and what surrounds us. Cosmology is ultimately the scientific form of that ancient human desire, the desire to situate ourselves inside existence. And perhaps this explains why people react so emotionally to theories challenging mainstream cosmology. Because these theories do not merely challenge equations, they challenge the narrative humanity tells itself about reality. And when narratives break, civilizations become psychologically unstable. This happened during the Copernican Revolution. It happened again during Darwin. It happened again during Einstein. Every major scientific revolution produces existential shock, and perhaps the cosmological crisis represents the beginning of another one. Good science requires humility, not belief, not ideology. Humility. The willingness to follow reality even when reality becomes uncomfortable. And this is why the cosmological crisis matters so much, not because it proves Jean-Pierre Petit correct, but because it reminds humanity of something essential. Science is not a frozen collection of truths. Science is a living process, a process built on doubt, contradiction, revision, and intellectual courage. The courage to question the model itself. That courage built modern civilization. And perhaps it may someday transform our understanding of the universe once again. Imagine for a moment that humanity eventually discovers a deeper structure beneath space-time. Not tomorrow, not next year, perhaps centuries from now. Imagine civilizations capable of navigating metrics the way humanity navigates oceans. Imagine distances collapsing, galaxies no longer isolated. Imagine looking back at the 21st century the way modern physicists now look back at medieval astronomy. Primitive, incomplete, still trapped inside an older framework. That possibility is both terrifying and beautiful, because it means the universe still contains hidden territory, and perhaps that is the most important message hidden inside the cosmological crisis. Not that humanity has failed, but that reality is still alive with mystery. And mystery is what drives exploration. Without mystery, science dies. Without unanswered questions, civilization stagnates. Without uncertainty, humanity stops looking upward. Maybe dark matter exists. Maybe future experiments will finally reveal it. Maybe the standard cosmological model will survive intact. Or maybe the universe is trying to tell us something subtle, something uncomfortable, something revolutionary. Perhaps the equations are incomplete. Perhaps space-time itself is stranger than Einstein imagined. Perhaps hidden structures surround us at this very moment. Or perhaps theories like Janus are simply another step in humanity's endless attempt to understand the cosmos. But regardless of the outcome, one fact remains undeniable. The universe is still far beyond our comprehension, and perhaps that realization is not a weakness. Perhaps it is the beginning of wisdom.